Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our fifth and final lecture covering material from Chapter 5. And this lecture begins with Hess's Law. And before we can really understand Hess's Law, we have to understand what a state function is. So I think the easiest way to visualize or understand a state function is to imagine climbing a mountain, okay? And let's make it a big mountain. We're going to climb Mount Everest, and there's two routes we can take. We've got we can go straight up the mountain. It's the least distance, or we can take this real long route that goes around the mountain, and that's a much longer distance. Now, the state function part of climbing this mountain is the change in altitude. So in either case, we gained the same amount of altitude. So the height at the top, minus where we started, would be the same. Now, distance, on the other hand, that is not a state function. So the distance to the top of that mountain does depend on the route you take. So applying this to chemistry, we're saying that enthalpy is a state function. And the reason that that's important is we can then, like in this example, we can find the delta H of a reaction by maybe going through an intermediate reaction. So let's think, for instance, maybe this our unknown reaction is very, very dangerous. Maybe it produces toxic gas, or maybe it's very flammable. But if we could do two reactions and ultimately end up at the same products, starting from the same reactants, well, we could use the delta H of those two reactions, and they would equal the delta H of the reaction as shown here directly. This was just something I happened to stumble on the morning of the lecture, and I made it into a slide. So I was looking in an old reference book and just looking at delta H values, and I found this pretty interesting. We've got two forms of carbon. We've got the graphite form and the diamond form. And if you remember, we call these allotropes, right? And it got me thinking, well, I wonder what the delta H is going from graphite to diamond. So they're, the two different forms of carbon. So let me show you how I can use Hess's law to solve this problem. So what I do, this is my unknown. I don't know the delta H, graphite to carbon. So I'm going to start here. I have one carbon in the graphite form as a reactant. Now this reaction with the delta H value also has one carbon, graphite form, as a reactant. So I'm going to keep it. Just leave this alone, okay? The other reaction has carbon in the diamond form, and that's what I need up here, but notice how it's a product. In this reaction, it's a reactant. Now remember, we can flip reactions, and this is perfectly fine. We just have to change the sign of the delta H. So if I make CO2 the reactant and the diamond form of carbon and oxygen the products, I change the sign of the delta H. And notice how I've got a product oxygen, one oxygen reactant. I can cancel those. I can get rid of them completely. Same with the CO2. It's a reactant over here, a product here. I can cancel those. And what I'm left with is exactly what I was looking for. I've got the carbon graphite form going to the diamond. So I sum my delta H values and I get 2 kilojoules per mole. This was a little bit perplexing to me. I expected a much bigger number. And so I think there's more to this, but we'll come back to that later. Great example of Hess's law. This is an example from MindTap, and it looks like a mess, but just kind of bear with me. I've got my unknown reaction down here. So I've got an unknown reaction. I don't know the delta H. I'm going to start with the first. I like to work left to right. Nickel oxide, solid form, one of these. I have it up here in this reaction. It's a product. So I'm going to flip the reaction. I did that down here in blue, and I changed the sign. Once I did that, I lined out this reaction. I'm done with this, okay? But I'm not done here because I need one NiO, and this is 2. So I can divide everything by 2. That's what I've done here, including the delta H value. I'm going to cross this off now, and I'm just going to box in this. I'm going to keep this reaction the way it's written. The next thing in here is the mercury liquid form, and I have mercury liquid form as a reactant like I need, but this has 2 in front of it. So again, I'm just going to divide everything by 2, including the delta H value. And then I'll box this in, I'll cross this off. I've got these 2 boxed in reactions, and I have 1/2 O2 on the reactant side here, the product side here. I can cancel those. I'm left with the unknown reaction. I can sum the delta H's and get the value. This problem was pretty tricky, and but I'm going to go through it kind of fast here. I've got my unknown up here. Same approach. I'm going to start with the N2. I have an N2 here, and there's only 1. I needed 2, so I'm going to multiply everything by 2 in this reaction, including the delta H, and then I'm going to leave this. I'm not going to change this again. The next is the oxygen, and notice how the oxygen's in 2 places, 2 different reactions. When I come across this, I'm just going to skip it. I'm going to move on, and hopefully this will all sort itself out. So moving on, N2O5, I need 2 N2O5s as products. I have 1 as a reactant, so I have to flip this reaction. So I flip the reaction, then I multiply by 2. That's written down here. I flipped it, changed the sign, then multiplied everything by 2. Since this one has a lot of reactants and a lot of products, you might find it useful to just, when you're done, list out all the reactants and all the products. And you might combine, like if I had 1O2 and 3O2, I could just combine and write 4O2 over here. That's not the case. But look at this. When I'm canceling, like my 2H2 reactants and products, those cancel completely. I've got 6 O2s here and 1 O2 here. So what I do is I completely cancel this one, and I just take 1 away from the 6. I'm left with 5 O2s. So this cancellation, oftentimes we completely cancel, like the HNO3, 4 and 4, but it's actually on a per mole basis. So if they're not equal, we can cancel the smaller one completely and just subtract from the bigger one. So these cancel, I get my unknown reaction, I can sum my delta H's, and that'll be the delta H of that unknown reaction. Enthalpy of formation is written as delta H with a little f. Sometimes we have this degree symbol. Looks like the f is right after the delta here. All the same thing, and by definition, this is the enthalpy change for the formation of 1 mole of a compound from its elements. So there's a couple examples down here. We've got CO2. I can write the reaction. I just need to make 1 mole of CO2 from its elements, and realize in this case the oxygen is a diatomic element, so that's written as O2, and we have to balance this, and we have to end up with 1 mole of CO2. Now this one is balanced, so that was easy, but sometimes we have to use fractions, so that we end up with 1 mole of product. The CCl4 example, we had to put a 2 in front of the Cl2 to balance that equation. And there's something really neat we can do with these, and we'll get to that in just a second. This is just a type of question you might come across on an exam, and it'll say, does this reaction represent the standard heat of formation for N2O4? And at first glance, and I'm looking at this one on the left, at first glance, I'm like, yeah, I got 1 mole of N2O4, but if I look closely, this is not an element here, so this is not correct. Over here, I wrote out the correct reaction, so I've got 1 mole of N2O4, and these are elements, diatomics, and we're all balanced up. So be prepared. That's a pretty common test type question. Now this is where it gets pretty interesting. I can use delta H of formation to calculate the enthalpy of a reaction. And this looks really busy, but this equation I'm going to use is basically I'm summing the delta H of the formation of the products minus the delta H formation of the reactants. And these products and reactant delta H formation values are usually given on a chart. So we'll have a chart and we'll have to look up the values and really be careful with signs, or states rather. I guess signs too, but the states, oftentimes you might have a value for water in the liquid state or the gas state. So be aware of that when you're consulting a chart. I got an example here, and I just pulled out the values and just put them into the question. So these are my delta H formations for the species in this reaction. So this reaction, I can calculate the delta H formation by taking the products. So I've got CaO, that's a negative 635.1, plus the other product, CO2, at negative 393.5, minus just one reactant here, and I've got the value. So if this equation had coefficients, we'd have to multiply these values by the coefficients. So these are based on 1 mole. In this case, everything was just 1 mole, so it worked out pretty good. But that's a pretty useful trick for getting the delta H formation of a reaction, because there are very, very many of these delta H formation values published in reference materials. So this really concludes chapter 5, and I put a couple questions in. Hopefully maybe you'll find these useful, just kind of reviewing some of the big things. So I'm going to start with this. Answers in the bottom right. Good one for you to practice. I've got gold added to water. So it looks like we want to find the initial temperature of the gold. So one of the things I noticed, it didn't say like gold dissolved in water or gold reacting in water. This is not a reaction. This is just two materials. This is going to be an MC delta T plus MC delta T equals 0 type question. This is a delta H for the reaction, and I'm given a bunch of reactions with values to solve the unknown. This is Hess's law. This is one you can work through. I've got the result down in the bottom right, negative 1628 kilojoules. Let's see if you can come up with that. This will be good practice. Hess's law problems are usually on the exams. And finally, the last thing I wanted to go over was this heating curve. And I just wanted to emphasize the importance of writing out a heating curve when we have one object that's changing temperature. And, if we have to solve for heat. So I'm just going to kind of point out a few things. Down here, we're in the solid phase. Now, this says heating curve for water. And notice how, so we're here where it's melting. We're at 0 degrees. That makes sense. Vaporizing or boiling, we could say, is at 100 degrees. So this is all solid down here. In the phase change, the temperature doesn't change. So I'm all solid here at 0. I'm all liquid here at 0. So right here, where this arrow points, where it's melting, we have solid and liquid present. This is just liquid up to here. Again, we're going another phase change. We're going from all liquid at 100 to all gas at 100. So, where this arrow is pointing, we have both liquid and gas present. Up here, just gas present. Really, really important to draw this out and use it as a roadmap if you're going to try to solve a problem. That's the best tip I can give you for that type of problem. So that rounds out chapter 5. Thanks for watching. Give the video a thumbs up and subscribe if you'd like to see more videos on the Professor DuBois channel.